Thanks everyone for joining today's webinar. So this is the second part of telco webinar series, mainly targeting end-to-end telco infrastructure. So the last time in the last webinar that we covered the transport network aspect of telco architecture, and in this webinar we will try to cover end-to-end telco domain, mainly focusing on fifth generation networks. Okay. Uh, so in this webinar, we will try to cover 5G new radio deployment models, and then 5G evolution and front-haul requirements, and also slightly on the transport network aspect of it and how we can cater stringent fifth generation network requirements in the transport network, and to cater 5G requirements. And then we will cover edge computing, especially multi-access edge computing in 5G and private 5G and its applications. And then we will cover 5G core architecture and its evolution and what kind of changes that we can see compared to previous evolved packet core networks on NFV. And then we will cover end-to-end network slicing aspect of it, and we will conduct another webinar, detailed webinar on network slicing in the upcoming weeks, but we will slightly cover the end-to-end network slicing aspect of it. Okay. So before diving deep into 5G network evolution, I will just do some sort of a primer, some sort of an introduction what 5G is again. So 5G is mainly has mainly three pillars, three KPI requirement that it created. So one aspect is enhanced mobile broadband, as you all know. So that's about increasing the network capacity, network bandwidth, and catering those throughput requirements. And the other aspect is massive machine type communication, that is like connecting millions of devices to a single cell site. So if you take LTE networks, then we used to connect like 100,000 devices, and with 5G it should be around 1 million. With sixth generation networks, it should be around 10 million, like that. So that's one of the key main requirements of pillars of fifth generation network. And the other aspect is ultra reliable low latency communication. That means we should be able to cater, uh, provide end-to-end latency at around 1 millisecond. So that's one of the key main pillars or areas in fifth generation networks. And on the right side, you can see a lot of applications. When it comes to 5G, let's say you want to cater latency, end-to-end latency is around 1 millisecond, at the same time around 1 gigabit per second throughput. Then the use cases are like tactile internet, doing remote surgery and all those things. So to cater those applications, you cannot do that with existing fourth generation of LTE networks. So there are a lot of applications that uh, make 5G evolution possible, and the business case possible. But the issue is it will take some time for this adoption in the telco network architecture. So and so in this slide, what you can see is where we are right now in terms of 5G evolution. We're currently at release 17, and very recently we got to see the release 17 related specifications, and we started with release 15, where we started deploying 5G networks based on standalone. That means we tried to connect LTE cores, EPCs to 5G new radio. And with release 16, we started seeing ultra reliable low latency communication deployments. And then V2X kind of scenarios, and then integrated access bridging and all that stuff. With release 17, we started seeing non-terrestrial network related specifications to use satellite communication links to do mobile backhauling and also front hauling, and also to provide rural coverage areas, provide coverage to rural coverage areas. With release 18, we're going to see more new advancements in fifth generation network related non-terrestrial networks, and also related to extended reality and all those things. So the specifications on the review and in the development. So by release 18, we can call it 5.5G or 5G advanced. So we are currently in that space. So if you take a typical 5G system, it should look like this. I mean, like from a very high level perspective, there should be next generation RAN requirement, next generation RAN part of it. That means the radio access network part of it, then the transport network part of it, and then core network part of it. And on the left side, you can see the applications or the end user devices. Then right side, you can see different packet data networks or PDNs that you get to connect to, right? So this is also similar in the LTE network as well. Like even in LTE, we used to have RAN networks, but in 5G, there are a lot of new changes in terms of the LTE protocol, 5G new radio protocol stack, and a lot of new improvements in transport network, and then the core network itself. So this is sort of a very high level diagram that shows how the evolution has happened over the years. And so if you take legacy systems, let's say in LTE legacy system, you used to see radio networks deployed with the remote radio heads at the cell towers and then baseband units at the bottom of the cellular tower. Then we connect to a central office or something. It depends on the operator, from operator to operator. And then we used to have IP MPLS based backhaul networks, transport networks, and also OTN and DWDM based transport networks. Then we connected to LTE cores at sort of a central site, and we started deploying LTE networks on dedicated appliances like IMS and EPCs. And uh, then with Cloud RAN, there was no stringent requirement on the transport and core networks. It was about taking a radio head, uh, taking the baseband unit to a central location, and we can call it a baseband BBU hotel. And then we connect multiple remote radio heads or RRUs or RRH to a baseband unit to save the BBU cost. And then by 2014, 2016, that time frame, we started seeing a lot of traction towards NFV and started deploying core network elements on virtual infrastructure as virtual network functions and virtual network VNFC as virtual machines are running on top of virtual infrastructure managers like OpenStack. And we started seeing early adoptions of segment routing MPLS, or migrating from existing IP MPLS infrastructure into SR MPLS, and also converging different control plane protocol stacks into BGP and using BGP labeled unicast. And then we started seeing early adoptions of IP over DWDM networks and phasing out some of the OTN layer networks and some traction towards IP over DWDM. And at the same time, the same years like 2016, 2017 timeframe, there was a lot of traction towards multi-access edge computing, even if 5G was not quite ready. And we started a lot of sort of a disruption in multi-access edge computing applications and bringing in user plane functions like user planes to the edge, and then centralizing RAN and all those advancements. But with 5G, the evolution continues the same way. We can see a lot of disruption in the radio domain. And we try to split the 5G new radio protocol stack into different components, and different components will take care of processing of 5G NR protocol stack. That means some of the lower fly processing will happen at the radio units, and higher fly to higher RLC layer processing will happen at distributed units, and then PDCP and RRC layer protocol, processing will happen at the central unit. So those are some of the key changes that we get to see with 5G evolution, and we will go through some of them in detail in the upcoming slide. So we also started seeing an evolution of transport network into segment routing V6 and also via V6 in the multicast domain, and also convergence of a lot of VPN technologies into a single VPN technology like EVPN, and it's a BGP address family. And then we started seeing deployments of, early IETF drafts for flexible algorithms to use different label spaces and IGP metrics to do network slicing. And then a lot of traction towards IP over DWDM kind of networks and flexible Ethernet. And then the core network started being deployed based on cloud native principles. So 5G core network functions are deployed as microservices, or let's say you can call it container network functions, and also IMS networks, network functions, 5G core applications deployed in that manner. So this is sort of a representation of current industry trends and also some reference from what is going on in the industry right now. I mean, like the early adopters of a lot of disruptive uh, technical advancement. And on the left side, you can see a typical 5G system. So we are seeing on the right side, you can see some of those deployments going on right now, like from Rakuten. They are deploying radio networks based on the principles of Open RAN. That means opening up radio interface between distributed units and radio units. So we're seeing a lot of traction in the market itself, and we're seeing a lot of operators deploying 5G DUs, DCUs, and CUs, and also 5G core network functions on public cloud providers like AWS Outpost. And this is what is going on in the industry right now, and a lot of traction towards deploying 5G networks on, I mean, like a lot of traction towards opening up interfaces and also deploying network functions on hyperscaler clouds, and also deploying network functions on a cloud native infrastructure. So this is sort of a representation of how an end-to-end telco network would look like from end-to-end perspective. So on the left side, you can see radio intelligent controllers for radio access network. We didn't see, we could not see radio controllers in the past for LTE. So there's a lot of traction with Open RAN initiatives to deploy near real-time and real-time RAN intelligent controllers. And then we are seeing a lot of traction towards private 5G, deploying private 5G in multiple mechanisms. Like, I mean, like we will go through the stuff in the upcoming slides. And then in the end-to-end telco infrastructure, then the 5G new radio deployments, and then fixed wireless access. That means it's also based on 5G. And in the middle, you can see IP transport networks and deploying segment routing, and also IP/MPLS core networks, deploying and also adopting distributed disaggregated chassis principles. And for an example, if you take operators like AT&T, they have already migrated their IP/MPLS infrastructure. 52% of their network is going on top of DDC infrastructure. We will not cover that aspect in this presentation, but later uh, webinar we will cover DDC concept as well, what it means. And on the right side, we can see the end-to-end telco network infrastructure is running on top of cloud native infrastructure. That means IMS and EPCs, and also 5G core network will run as container network functions, and also IPTV headends, and everything being deployed as microservices. And on top of that, you can have some sort of a fabric orchestration and management system to manage your network infrastructure. And then on top of everything, you need to have some sort of an end-to-end orchestration system to manage and orchestrate uh, different network segments. And on top of that, you can have a next generation OSS or PSS system where you have orchestration functionality pre-built in. Okay, this is sort of a capital expenditure slide of telco, just to give you an understanding where the fifth generation network investment goes in. And most of those telco operators are deploying there are a lot of investing a lot on fifth generation network upgrades and all that stuff. And from this side, you can see most of that investment goes in the direction of access networks, and to do site acquisitions and new site deployments and rollouts and all those things. And we are seeing a lot of traction towards IT and software ecosystem as well, like building new data centers. And because telcos have to adopt cloud native principles and build cloud native infrastructure. So there's a lot of traction towards this one as well. So we are seeing a lot of capex investment. So this is sort of a report that I have taken from Omdia. So they have taken the capex investment of top 10 telcos in the world, and which areas that they invest mostly in. So yeah, at the same time, you can see some big investments on WDM side as well to build metro WDM networks and to invest in optical fiber backbone. So we will get into 5G new radio deployments, how we can do 5G new radio deployments. There are 7 options in deploying 5G new radio infrastructure. There are 2 main mechanisms that we can deploy 5G new radio. One is non-standalone, and another one is called standalone. So what it means by non-standalone means you'll be connecting 5G G node B directly to a world packet core node. And in standalone, what it means is we will connect 5G G node Bs and also E nodes Bs with the support of 5G new radio protocol stack. That means a PDCP layer will come from 5G new radio protocol stack. So that means it would be NRPDCP. And so we will connect LTE ENBs and also GNBs to a 5G core. So that kind of deployment, we call it 5G standalone. So the most popular option or configuration of deployment 5G right now is option 3. And under that, there is an option called option 3X. So that's what you can see over here. So we will connect 5G G node base to an E node B, and then the E node B will connect to an EPC. So this E node B will work as a master RAN node, and G node B will work as a secondary RAN node. The most popular option out of all this is deploying 5G new radio in non-standalone mode as option 3X, where you will have MCG means a master cell group and SCG means a secondary cell group. So we will deploy it as MCG and SCG split layer. So that means you will terminate master cell group. That means number of frequencies that you will use in an E node B, and you will aggregate all that information and do the processing. And so the MCG bearer, at the termination of the stream or packet processing stream will happen at ultra MAC only. That means the master node, and the CG split bearer, you will do the NRPDCP processing at the secondary node, and then some part of it will go to the 5G G node B, and the other part will go to ENB ultra MAC layer. So that's why the option that is the option 3X, and this is this is the most popular way of deploying 5G in a non-standalone mode. So if you deep dive into 5G new radio protocol stack, this is quite similar to OSI layer TCP or OSI layer or TCP/IP protocol stack. So it consists of non-access stratum messaging and part of it on top, and then we have protocol data service data adaptation layer, which is quite new in 5G new radio. I mean, compared to LTE protocol stack. So the main function of SDAP or service data adaptation protocol is to do QoS management. And then we have PDCP layer. PDCP layer take care of header compression and also encryption, DLT. And then RLC for automatic repeat request, and also MAC for hybrid ARQ mechanisms. So we will go through some of those stuff when we go deep into 5G new radio and also core network webinar. And also the file layer. So this is how file layer will take care of, I mean, like file layer itself is a very deep, I mean, like there are a lot of functions to file layer, like doing scrambling, modulation, layer mapping, pre-coding, remapping, IQ compression. So there are a lot of functions to those layers. So this is how typical 5G new radio protocol stack would look like. So usually in the past, the baseband unit of a radio took care of this, I mean, like those layer processing, especially PDCP, RLC, MAC, and file layer processing. But with 5G, there is a new layer called SDAP for user data processing and also QoS management for the user plane. And then there are some new addition to non-access stratum messages. That means usually non-signaling will happen between the user equipment and also between the AMF functions of the 5G core. So we will go deep into the 5G fronthaul. So in the previous slide, we explained how the 5G new radio protocol stack looked like. So the 5G fronthaul is a new requirement came with 5G because we need to do we need to carry radio samples over a transport network. To do that, I mean, like when we, I mean, like because with 5G, uh, because with 5G we have to carry a lot of radio samples over a transport network, and we will be going with higher MIMO configuration, higher carrier aggregation configurations, and all that. So to do that, we need to bring some processing functions away from the radio unit. So in the previous generations, we used to do the split at the option 8, and with 5G there are multiple options described, and the most popular one is option 7 and option 2. That means we will do some part of, I mean, like lower 5 processing at the radio unit, and we will do uh, DU processing at, I mean, upper phi layer and to upper RLC layer processing at the at a node called distributed unit, and then we will do higher layer processing at a central unit. So those are the configurations that we can go with 5G. The main reason is because we need to carry those in phase and quadrature samples over fiber link, and you will not be able to cater those capacity requirements and latency requirement if you do go with option 8, mainly sorry, mainly capacity requirements. So so this interface between uh, lower 5 processing and also higher 5 processing equipment, that means the RU and DU, is called front hole, and between upper RLC layer and PDCP layer, we can call it mid hole. So there are multiple configurations that a telco operator could adopt where they want to deploy their DU and CU equipment. And also there are new standards from uh, Open RAN or RAN Alliance on opening up those interfaces, because some vendors usually do their lower file processing and higher file processing stuff differently, because higher file layer itself has a lot of layers to it. So depending on where you split up those sub-layer components, the supporting third-party DUOC will differ, right? So there is a disadvantage in there. So that's why Open RAN is there. They came up with those specifications, and there are multiple specifications, and how you would build that specification. That means how you would carry information radio samples over a fiber link. So we'll do sort of a primer on Open RAN as well. So the main purpose of Open RAN was to bring that interoperability between different vendor DUs and CUs, and there are a couple of goals, like bringing in openness and also RAN virtualization and economies of scale. That means you can take hardware from any vendor, okay, any hardware vendor, and then you can take software. That means NR protocol stack or LTE protocol stack from any vendor, and you can do mix and match from different radio unit vendors and DU vendors. So if you look at current market share of, I mean, like if total RAN market share, 6% of RAN market share goes to Open RAN. That means operators have already started deploying Open RAN. There's huge traction toward ORAN as well, but the issue is because most of the telcos have already made 5G investments, so we are not seeing huge disruption. I mean, like huge uh, market share growth compared. I mean, like uh, compared to the early days of Open RAN. But with sixth generation networks, we'll definitely be able to see big market share going to those new radio Open RAN vendors. And this is sort of the architecture side, how NORAN interfaces would look like. Okay, I mean, like an Open RAN implementation would look like. So to Open RAN itself, there has to be, I mean, like the interfaces has to be there, and then on top of that, you need to have some sort of a controlling mechanism they have introduced, and they have introduced new interfaces like E2 and A1, and also new RAN controllers like uh, RAN intelligent controller. That means it's running some sort of an SDN control. On top of that, you can run different radio resource management applications and mobility management applications, QoS management applications like that. So there are two types of RAN intelligent controllers. That means near real time RIC, and also non-real time rigs. Okay. And so there are a lot of vendors, okay, that support Open RAN. So the other aspect that we have to look at is when you're deploying a disaggregated radio access network. That means if you split up 5G new radio protocol stack and do processing at different locations, then you need to carry that traffic over some sort of a transport medium. So that's why we need to build a front haul network, which we did not see in previous iterations or telco network generations. And to do that, we need to build front haul networks. So there are a lot of options. We can build a transport network. One option is going with IP Ethernet front hauls, and then or maybe going with passive WDM networks. Okay, so there are a lot of options that we can build those front haul and mid haul transport networks. One option is going with passive WDM. Another option is going with active WDM. And also we can consider GPON and NGPON too, but the issue is if you have very stringent timing requirements, because it is an asymmetric link where you will have different uplink and downlink speeds and also time allocation. So GPON 2 and GPON 2 is not a very good option if you have very stringent requirement on latency and also on timing accuracy. And then IP Ethernet, uh, using IP Ethernet equipment as front haul is another option, good option, because you have OEM functionality and also uh, you can get equipment at a cheaper price if you go with uh, disaggregated options. And also you can consider using direct fiber to connect radio equipment and also DU equipment. So there are multiple options. So a lot of operators are exploring those domains and what they can do. And it totally depends on the operator's fiber infrastructure layout and also the capex investment. I mean, like if they have fiber presence and they have already uh, optical network presence there, then it depends on what kind of network layout they have at the edge of the network. And we will also touch upon the 5G synchronization aspect as well. So when we move towards 5G, then we have very stringent requirement on timing accuracy. So in the past, we used to distribute frequency and timing information through two protocols, especially one is SYNC-key. It's a 5-layer protocol. And then I used to use PTP or IEEE 1588 version 2, and also latest version is version 2.1. So if you are building a 5G network, then there are a lot of aspects that you have to look at. One aspect is whether it supports G.827.1. This is an ITU specification. So that means full path timing support, that you would be able to carry timing information from the uh, grandmaster or PRTC towards the edge of the network. Then G.827.5.2, if you have PTP unaware network in between, then this profile could be supported to that area domain. But with 5G very stringent timing requirements, then you can go with APTS. It's another mechanism where you can connect some sort of a GNSS receiver to a boundary clock at the edge to do clock recovery or to compensate for errors that could occur in between when you're providing timing information. And the other aspect is when you are considering distributing clock information from the PRTC towards the edge of the network, then you have to consider boundary clock timing accuracy performance. That means there are multiple classes. The specification is G.827.73.2. And for 5G new radio requirements, then it has to at least support Class C timing. That means you need to have continuous timer at around 10 nanoseconds if you want to do coordinated multipoint and joint transmission and all those higher MIMO configurations and all this stuff. Then the Class C timing is required, and Class D timing specification is already underway. So those are some of the main areas that you need to focus on when you're building a transport telco network. And the other aspect is whether the front haul networks can support 802.cm, that means time sensitive networking, time sensitive networking profile for 5G front haul. And there are two profiles, profile A and profile B. So what they actually do is they provide, I mean, like in profile A, we find strict priority queuing, and also in QBU preemption. That means when you distribute traffic based on the QoS levels, whether you would do preemption and all that stuff. So this is some those are some standards that you need to follow when you're building a 5G front haul network. So another aspect in telco architecture evolution is multi-access edge computing. That means bringing edge computing. That means computing to the edge. That means we used to do. I mean, even with current telco network architectures, we used to have uh, telco clouds at central locations. With 5G, because of the latency requirements, we need to bring computing to the edge, or telco applications to the edge. So multi-access edge computing is part of a big domain called edge domain, edge computing. So MEC is part of edge computing, and we can use the umbrella term. I mean, you may have heard of fog computing as well. Fog computing means that if you take computing from the central location towards the far edge. So that's the umbrella term. And because for computing, I mean, for computing itself implies if you have some sort of a computational power on IoT devices itself, or maybe far edge devices as well. So that's why it's an umbrella term. Under that, you find edge computing. Then under that, make multi-access edge computing, because multi-access edge computing is part of edge computing, and it's a sort of a ETSI MEC. It's an ETSI, European Telecommunication Standard Institute's Industry Service Group, ISG, which came back in 2015, 2016, the time frame. So see, and also this is closely aligned with ETSI NFV Mano reference architecture. And the main objective of ETSI MEC is to bring applications to the edge and to expose certain APIs for application developers to develop applications based on the sort of information that you get out of the telco networks. Okay, so this is how the reference architecture would look like. So there are a lot of reference points defined. This is quite similar to CNFE Mano architecture, and also it's based on CNFE Mano architecture. So we find MEC platform. That means for an example, if it is an OpenStack deployment, let's say if it is a Kubernetes deployment, so MEC platform itself means something like that. Then you need to have some sort of a platform management software, and then MEC host is where you would host the multi-access edge computing platform. And on top of that, you can have different MEC applications, and you will expose certain APIs. And for example, this like MP1. So this interface that you can see over here, so you can expose radio network information, location related information, traffic management information, and all those things through those APIs. So those reference points are already there. And there are a lot of APIs defined by ETSI-MEC ISGs, so you can make use of them to build your own application. So there's a lot of big ecosystem growing around multi-access edge computing to make use of those APIs, and to provide different services for different technical requirements. So this is sort of an application already. This is an old slide, but I mean, old architecture of SK Telecom, how they have deployed multi-access edge computing. So they also have MEC management portal, uh, and also MEC platforms, and their current platforms are based on Kubernetes and running different types of services on the MEC platforms. So this is how things look like in a typical MEC deployment. And another aspect, I mean, private 5G, another aspect of telco evolution is private 5G. I mean, private 5G in and itself is not a part of telco architecture. It's sort of a big application. I mean, like the most prominent application when you're deploying 5G. I mean, when you're going from fourth generation networks to fifth generation networks, the biggest issue that you would face is that you need to find a new revenue stream. So private 5G would be uh, the most prominent application in the upcoming years. And many telcos have already started deploying private 5G solutions and providing private 5G solutions to customers. So what private 5G means is something like this. I mean, you will try to bring 5G network mobility core uh, functions to the edge of the network. That means, let's say there's an enterprise or a manufacturing enterprise requirement to build their network and with support of security and lower latency, and to if they have more like applications like mobility applications, moving equipment or vehicles, and if they have very stringent requirement on quality of service, then the private 5G is the option to go for, where you would bring 5G mobility core to the edge of the networks. That means you will deploy 5G in a box. That means you will take 5G core, AMF, SMF, and all those network functions to the edge of the network, and we'll try to build a private 5G network. So there are few options that you can deploy. Like there are few configurations where you can deploy private 5G, and bringing 5G core components to the edge is called standalone. That means NPN standalone. We use the term non-public network to denote private 5G. That's the 3GPP term that we use. And the reason why private 5G is much better, much more popular in manufacturing and industrial use case is because of those reasons, and compared to Wi-Fi, and because in Wi-Fi you will not get comparatively good security compared to a mobility core, and also you will not get radio interface latency, SLOs, service level objectives met with Wi-Fi. And then if you have very strong mobility requirements and QoS requirements, then instead of going for Wi-Fi 6E or Wi-Fi 7, then private 5G is the best option to go for. And so this is sort of a representation of how private 5G deployments would happen. And we usually use the term NPN on public networks to denote private 5G. So if you are deploying a separate 5G core at customer premises or something like that, when you use the term SNPN. And then another term coined by 3GPP, which is called PNI. NPN, that means you will deploy some radio functionality. That means you will have radio network and also user plane function at the customer edge, and then you will carry core network functions to the central locations of the mobile network operator. And the other uh, deployment is providing private 5G with network slicing, and this is the most like in this geography, and from capex perspective, this is the most cost effective to go for. That means you will take a 5G network slice from the operator, and then you will deploy a private network. That means you don't have to invest on 5G core network, small 5G core network, or other equipment. So there are a couple of options, and on the left side you can see where we are right now in private 5G. So this is 2021 infographic representation from I have taken from NetManias. So many operators all over the world have started releasing spectrum for private 5G applications, especially in FR1 frequencies, that means sub 6 gigahertz frequencies, as well as in millimeter wave frequencies. And the other thing is, in this diagram, you can also see the state of private 5G deployments all over the world. And and currently, the most popular way of deploying private 5G is based on CBRS spectrum. That means uh, that you will be controlling the spectrum allocated for certain private enterprises or organizations through some sort of a spectrum allocation server. And there are multiple tiers for that spectrum allocation. So lowest tier is generic access license, and then priority access licenses, and then some regulated tier 1 licenses. So you can get any frequency band. Like in CBRS itself, CBRS was recently renamed as OnGo by CBRS Alliance, and as now as OnGo Alliance. So you can make use of some sort of a spectrum, let's say 80 megahertz to 150 megahertz spectrum, allocated from the central spectrum allocation server based on your requirement, if you don't have any interference from another private 5G deployment or private 5G deployment nearby. So this is the state of the current private 5G deployments all over the world. Then we will dive into the 5G transport network aspect of things. And in the last presentation, we covered a lot of things related to transport network. So we will not go very deep into the transport network aspect in this webinar. So this is how a typical telco network, transport network would look like. So usually they have fiber infrastructure. On top of that, they have DWDM and RTN layer. And then on top of that, you can have metro IP access, metro IP aggregation, and IP MPLS core infrastructure. Then you can have microwave infrastructure, then passive optical network infrastructure based on gigabit passive optical network. And you will connect your radio networks to the core network in this manner. And then you can have multiple element management systems from different vendors. So this is how a typical traditional telco infrastructure would look like. And with 5G, we have to cater a lot of requirements in 5G to cater latency and throughput requirements. So we need to have uh, a lot of improvements in the 5G network. That means introducing fronthaul, for example, introducing fronthaul. So that's what is represented over here between radio units. And I mean, we talked about this in detail in the last couple of slides. So we need to build, from a transport network perspective, we need to build 5G fronthauls to cater those uh, requirements, especially related to URLLC requirements. And then we need to have adopt segment routing. I mean, for an example, if you look at three main pillars of 5G, the URLLC and BB and MMTC, usually EMBB and MMTC can be catered with current telco transport networks. So we don't have to specifically build transport networks to cater those, apart from fronthaul requirement, where you have to carry very large throughputs because you have to carry IQ samples, interface and coordination samples, radio samples, so some sort of an infrastructure. Apart from that, then you have no stringent requirement on the transport network. But for ultra reliable low latency communication, you need to have uh, some technologies in place to cater those. One aspect is to build 5G fronthaul. So you can build controls as we explained in the last couple of slides using different technologies, WDM, IP Ethernet, and things like that. And then you need to adopt segment routing traffic engineering, and segment routing flexible algorithms, and also technologies like flexible Ethernet, where you will insert some sort of a shim between PHY layer and the Ethernet MAC layer, and PCS and PMD layer. Uh, so there are a lot of candidate technologies to that, and so we need to cater those things if you are building a 5G transport network to cater 5G requirements. And then over here, this is sort of representation of, I mean, like if you are deploying segment routing in the network, then you need to have segment routing path computation elements, and then some sort of a hierarchical path computation element to support end-to-end path computation. So standardization is already going on. And then you need to have some sort of an IP and optical domain orchestration to do configuration automation and orchestration. And also the end goal is to have some sort of closed loop automation system all the way down to do network management and orchestration part. And so those are the things that we need to see in a future transport network from a telco's perspective to adapt to 5G requirements coming from the radio side and also from the core network side. So this is sort of a high level overview, and we went through this one in the last webinar as well. So we need to look at IP, Ethernet, and L2 and above layer evolution. So we need to think about how you could adopt Flex Ethernet for Flex OT, and depending on the requirements, whether it is a good good choice to go for if you want to do network slicing as hard slicing in the PHY layer. And and the other aspect is you have to look at Sigma routing MPLS and XRv6 deployment strategy. So how you would deploy segment routing traffic engineering, path computation element, flexible algorithms, and how you would do segment routing v6 compression and all those things. And also how you would do MPLS interoperability. And then you have to look at how you would evolve existing L3 and L2 services towards EVPN. And and the other aspect is we talked about, I mean, like in the last webinar about near packaged optics and co-packaged optics. That means you will take silicon photonics uh, uh, chiplets, and I mean you will create, I mean like many vendors have come up with those silicon photonics to get rid of uh, transceivers. So we will in the future, in let's say next 5 to 10 years, we will start to see network equipment without transceivers, specifically built transceivers, and then a lot of traction towards open networking, and how we would evolve DWDM and OTN layers, and whether you need to keep DWDM and OTN networks, especially OTN networks. And then there's a lot of traction towards IP over DWDM, and then open optical technologies and the evolution related to open ROADMs and open transponders. And because there's a lot of traction towards building equipment, I mean, like software separately and hardware separately. And so there's a lot of traction in that domain. And how we would build 5G fronthaul networks. And we talked about this one in detail in the previous slide. And then you have to look at network management and orchestration, and also how you would do network telemetry, how you would do performance measurements and all that stuff. So, and also software defined networking. So those are the areas that you need to focus on in an end-to-end telco transport network. And then we will go into 5G core network. So if you look at previous generations, this is how things used to look like. We used to have different core network functions moving from 2G to 3G and also 5G. And in 4G, we used to deploy those network functions on NFV. I mean, like very recently. I mean, very recent years. And then with 5G, we are seeing sort of a big paradigm shift. We will talk about that one in detail. So we will move on to the next slide. In 5G, we usually use the term service-based architecture, and compared to the previous generations. And if you take 4G LTE, we used to have a reference point based architecture for LTE. That means you used to have a lot of network functions and connecting with the network functions based on different reference points, and especially based on protocols like diameter, GTP, and different protocols. But with 5G, we are seeing a big paradigm shift. We are deploying different network functions, really, I mean, like 5G network functions as microservices, and especially 5G control plane. That means functions like AUSF, access and mobility functions, and then session management functions, and then charging functions, UDM, and there are a lot of new functions in 5G core network. So we will deploy them as microservices, and each and every network function will work as different service, I mean, like service consumer and also as a service producer. So we will be exposing RESTful APIs between those network functions. So that means you will extract information or request and subscribe to information through RESTful APIs, like RESTful get and post and put and delete and all those RESTful functions, HTTP methods, sorry. And so this is how 5G core network would look like. And so we call this kind of architecture service-based architecture. And we get the flexibility to deploy them as microservices. And if and we will talk about other aspects and what are the use cases and advantages of going in this direction. So this is sort of a high level, detailed overview of a 5G core network. So we can split the 5G core network into three different layers. One layer is control plane functions. We're deploying as microservices, then data plane functions. So in 5G core network, we usually the data net user plane function is the data plane function, and in the LTE core network, we used to have P gateway and S gateway. So in 5G, we have combined both together into a user plane function, and we have taken S gateway control plane and P gateway control plane to a function called session management function. So this will take care of session management and also policy enforcement, policy uh, enforcement with, I mean, like using a policy control function. And in 5G core network, so we will deploy all those services on top of cloud native infrastructure. So it means that those container network functions can be deployed on top of Docker, or could be CRIO, or could be containerd, any kind of container. And then we can have some sort of a service mesh between different core network functions. It could be based on STO, it could be based on link code. So it depends on the operator's preference. So you get more security for deploying service meshes in the core network itself. And also IMS core functions can be also deployed as cloud native functions. So this is how a typical telco core network would look like. And so we will get into network slicing, and this is also another new application of 5G network infrastructure, and one of the key hot topic in 5G. So what it means by network slicing is being able to allocate different network compute, storage, memory, and management resources on different network domains. And so we call it network slicing. So in network slicing terminology, because there are a lot of 3GPP defined terms and 3GPP defined specifications to explain how we can do network slicing. So we usually use the term network slice instance to denote a network slice. And each domain, let's say next generation RAN or transport on 5G core network, can have some sort of a network slicing subnet instance. So network slicing subnet instance uh, is a pool of resources, compute, storage, memory, management resources. Usually this one would apply for next generation RAN and also 5G core network, not specifically for transport network, because transport network standards are not defined by 3GPP. And what you can see is we can take network slicing subnet instance and from, let's say, a radio network, and we can put together we can group different NSSIs from different network components, and we can call it a network slice instance. So usually a network slicing subnet instance can support a different scheduling and also carry aggregation and duplication and dual connectivity options for the radio network. And in the core network, we will allocate different control and user plane functions for the NSSI. So that's how things would work. And for the transport network, usually there is no defined NSSI, but we can come up with those abstractions to allocate certain flexible algorithms. And if you want to build a sort of slice based on IGP metrics, and also to do SRTE and QoS allocation. So we can specify those things using certain abstractions. And in 5G core network, we find a specifically assigned function called network slicing selection function in the 5G core network, which will take care of a network slicing uh, allocation, network slice allocation to different 5G core network nodes, as well as the user equipment. So usually the access mobility function is similar to mobility management entity in 4G LTE core, and it has the mobility function in it, and it will query when there's a requirement for network slicing. Will query network slicing selection function to select whether it has the capability to be part of this network slice, and which AMF it should use in the UE registration procedure. And it will look at the load of the network slice through network data analytics function, and it will take those information through those different RESTful APIs defined over here. And there are reference points already defined for that one as well. So as for being part of a network slicing. And there's another term in network slicing called network slicing selection assistant information. So what it means is is how you define a network slice. Let's say you want to be in enhanced mobile broadband slice, then network slicing selection assistant information will contain that information. Typically, a user equipment can subscribe up to 8 network slices simultaneously. So each network slice can be called, I mean, like the identification name can be coined as SNSSAI. That means single network size selection assistant information. So there can be up to 8 network size selection assistant information associated with it. So each NSSAI can have sort of a slice service type. It's 8-bit value, and also 24-bit value for slight differentiation. So based on that, you can have multiple combinations. That means you can have up to 255 slice service types, and then multiple 2 to the power 24 minus 2 slice differentiator values. Okay. So we will go through network slicing really in detail in the upcoming webinar. Really deep in how we can how network slicing can happen on radio resource level and also on core network level and also transport network level. So this is sort of a high level representation how we would do network slicing. So that means if you have some sort of an ultra reliable low latency requirement to cater for a certain application, or let's say you have some requirement uh, to have very high bandwidth and you need to connect multiple devices or like that. So you can specify different SNSSAI, single network size selection assistant information, with slice service type and slice differentiator. And then we can allocate different resources on the radio network, core network, and also in the transport network itself. So this is what it means by network slicing. So we have come to the end of the presentation. So if you have any queries on certain things, uh, you can ask me.